Okay, Section 5 GPU computing systems with Grace Hopper, Grace Blackwell superchip, and the GPU computing systems with AMD MI250X GPU and the MI300A APU. We are going to have a look at the GPU computing systems with all these products. So let's start with the Nvidia Grace Hopper. Is announced March 2022, the Grace Hopper. And later on, NVIDIA also announced the Grace Blackwell. Grace Blackwell is very much similar to the Grace Hopper. It's the next generation of Grace Hopper. Okay, for these two series of products, there is a very important evolution. It seems that CPU is not anymore a PCIe equipment, but a coprocessor. Okay, these are two questions because I have the question marks here. Okay, we are going to go through the technical details, a little bit technical details, and at the end, I'm trying to draw my conclusion whether is no more a PCIe equipment, but a coprocessor or not. Okay. We won't dive into too much details with the Grace CPU or the GPU. We are going to focus on the interconnection between the Grace CPU and the Hopper GPU. And we are going to also have a look of these interconnections between the GPU and the NVLink network and the Grace CPU to the high-speed network. But that's not the focus. The focus is the Grace CPU and the Hopper GPU and their interconnection. And this one will be discussed in the next section. But this section, we are going to focus on this one. We pass these technical details of the Hopper GPU. We focus on the links on the communication. So here, the first thing is that we can see that there is the NVLink 4 and the PCIe for the Hopper GPU. Okay. So there is the NVLink 4, which is used to connect the Hopper GPU to the NVLink network. And where is the PCIe? It has to be here. There is nowhere the PCIe has to be. There is the PCIe link between this Grace CPU and the Hopper GPU is generation 5. There is the PCIe link. And then there is also this NVIDIA NVLink C2C. C2C means nothing, it's chip to chip. So we have this NVLink 900 gigabytes per second. That's between the Grace CPU chip and the Hopper GPU chip is C2C. Okay, so this is the link between the two chips. And there is also this hardware coherent interconnect between the Grace CPU and the Hopper GPU. So because we know that the PCIe protocol, it doesn't have this kind of coherent protocol. There must be something else running on top of this NVLink. So there is the second protocol running on top of this C2C, which is kind of cache coherent protocol. Cache coherent protocol between the CPU and the GPU. And at the end, what we have is the extended GPU memory feature enables the Hopper GPU to address all CPU memory as GPU memory. Each Hopper GPU can address up to 680 GB of memory within a superchip. If we do a math, 608 equals 512 plus 96. So that means the GPU can access its own memory and also the memory of the CPU. So the total memory. This is called EXG, extended GPU memory. Okay, we are going to have a look at all these four features, four stuff, and then we are going to draw a conclusion. Okay. So the evolution of the NVLink is in step with GPUs. This is the slide. This slide comes from the slide stack that Nvidia presented in the 34th hot chip meeting. This slide shows that since 2008 and 16, the Nvidia has been evolving this NVLink technology. At the beginning, we have 4 links between a pair of GPUs, and each link is 40 gigabytes per second. And later on, the NVLink 2, we have 6 NVLinks between 2 GPUs, and you have 50 gigabytes per second, and you can reach 300 gigabytes per second total between the 2 GPUs. And then 2020, you have NVLink version 3, and 2022, you have this NVLink version 4 with 18 NVLinks, 50 gigabytes per second each link, and you have 900 gigabytes per second in total. So if we come back and have a look at this one, this is exactly NVLink 4. You have 18 links, NVLinks, and you have 900 gigabytes per second in total for this link here between the Hopper GPU and the NVLink network. Okay. Another slide I have taken from the same presentation is this one. The presenter made a mapping to the traditional networking to make things easy to understand. If you look at this one, you have these traditional OSI layers. You have 7 layers, and you have some other features, unique offload, all these offload features. Okay, if you compare the NVLink with the traditional Ethernet internet, and we have this custom firmware OSFP, which corresponds to this physical layer of internet communication stack. And we have this NVLink custom on-chip hardware and firmware, and also this one, they are correspond to the Ethernet, the data link layer, and the transport layer. And we have this one, the NVLink network addressing and management protocol, which correspond to the IP layer of the internet network. Okay. We need to come back to this one for our discussion. We are going to have a look at this C2C link. This C2C link here, this is the C2C link. Is I mean, if you look at this the links here is this C2C link. You have 18 NVLink 4 and 900 gigabytes per second. C2C just means that's chip to chip. It doesn't mean anything else. Basically, this C2C is the same as this NVLink 4. It's the same thing. And I think this NVLink C2C, the NVLink C2C that has been used to connect the Grace CPU and the Hopper GPU, it should cover these 4 layers. The C2C link should cover these four layers. I have a question mark here because I am not sure I'm correct or not, but I want to express my point of view. I think that covers these 4 layers. I have tried to find out the answer, but I didn't find anything available from the internet that does explain that my understanding is the correct one. But here is that my understanding is that the C2C link covers all these layers. Okay, and these are the communication network. And on top of this C2C, we have 2 protocols. One is the PCIe generation 5, and the other one is the cache coherent protocol. And this protocol is going to make this super chip works. We are going to have a look at these protocols. Okay, so let's move on. So this is this is showing the mapping of the NVLink to the Internet protocol. I think on top of the C2C, we have this PCIe Generation 5 protocol running. Sorry, this is P, and we also have this kind of cache coherent protocol running on top of this C2C. Okay. Oh, this is the cache coherent protocol between the Grace CPU and the Hopper GPU. Okay, Grace CPU and the Hopper GPU. AMBA CHI, this is the protocol. This is the cache coherent protocol comes from ARM CPU because that's reasonable because this Grace CPU is the ARM CPU and Nvidia has licensed this ARM technology uh, from ARM. Okay, so what does that mean? AMBACHI stands for Advanced Microcontroller Bus Architecture Coherent Hub Interface. This is the cache coherent protocol from ARM that's used to connect all the system components. Okay. Between the ARM CPU and the Hopper GPU, we have this famous NVLink C2C. And this is the physical communication communication links. On top, there is going to be the cache coherent interconnect running, which for our case, this is the AMBA-CHI protocol running on top. Okay, how does that work? Let's just go through this one and try to understand how it works. Okay, so if the GPU wants to read virtual address, okay, and virtual address. Okay, is going to try first from the cache. Okay, it tries to read this virtual address. It tries this cache, and you have cache misses. Means that it's not in the cache. It has not been cached. So then the GPU is going to check this translation look aside buffer. Try to understand whether this address has been translated into the physical address. Okay, there is a hit, means that this virtual address has been translated into the physical address. Okay, if it has not been translated, the GPU, the Hopper GPU is going to try use this ATS to translate this virtual address into the physical address. So here it's the ATS stuff. ATS stuff will be discussed later on, but you just remember that first is going to look at this translation look aside buffer to know whether this translation has been done. If it has been done, that's okay. If it has not been done, it's going to get help of the ATS service to do the translation. We are going to come to this ATS stuff later on, but right now there is a hit. That means this virtual address has been translated. Then you have got this translation, you know where the data is. The data is located in the CPU side, in the Grace CPU side. Then the Hopper has to ask the CPU. Basically there is a unit which is called GPU memory management unit. The GPU memory management unit is going to issue a request, direct memory request. to the CPU, and the request is going to be over CCI, the cache coherent interconnect. And for now, the cache coherent interconnect is the NVLink C2C. So the DMA request is going to go through this C2C and send to the other side, send to the CPU side. Okay, and then the CPU said, receive this request. The CPU said that the CPU is going to receive the request, is going to find out this cache line. Oh, okay, the GPU is asking for this cache line. I know where is this cache line. I can find it. I'm going to send this cache line back to the GPU, and then the CPU, from the CPU side, I mean from the host is going to send this cache line back to the GPU. Again, this is going to go through this NVLink C2C, this famous NVLink from Nvidia, and the cache line will be sent over through this NVLink C2C to the GPU. The GPU is going to receive this cache line, and the cache line should be managed by this GPU memory management unit. And this management unit is going to receive this cache line and is going to put that into its cache. So it should be cached by the GPU. So what we have seen is that the GPU need to access some data. The data is not in its cache, but it has been cached by the CPU. At least it has been. At least is in the CPU's physical address, physical memory address. So then the GPU need to get the data from the CPU. Then the CPU need to get the data from the memory if it has not been into the cache. Now, basically, if the data has not been put into the cache, the CPU need to read the data and put in its cache. If the data has already been put in the CPU's cache, it's fine. And then the CPU need to send this cache line to the GPU. By this synchronization, right now, after the cache has been received by the GPU, we know that the cache from both the CPU side and the GPU side, the cache right now is coherent. This is the work of the AMBA-CHI protocol, the cache coherent protocol. That's its job is to guarantee the cache coherent between the CPU and the GPU. So right now we know on top of this NVLink C2C, there is the cache coherent protocol running. Okay. Now let's move on. Let's move to the ATS stuff. For the traditional systems with the Hopper GPUs connected to the x86 CPU, suppose this is x86 CPU. If you have your GPU connected to the GPU by PCIe traditionally, if there is no ATS service, that means the CPU and the CPU have independent process page table, and the system allocated memory is not directly accessible from the GPU. When a program allocates memory with the system allocator, but the page entry is not available in the GPU's page table, then accessing the memory from a GPU thread fails. So this is the situation. If you now this is the GPU page table. If the GPU wants to access the memory, the page table is going to do the translation from the virtual address to the physical address, and then the CPU can read from the physical address the data. The same story happens with CPU. If it needs to read a bit of data from the memory, the translation will be done by this page table, and then it can read this memory, and it is going to get the data. But the fact is that with this kind of PCIe link between CPU and GPU, if there is no ATS, address translation service, then there is no possibility for the GPU to access the CPU's memory. Is not possible, and for CPU to access the GPU's memory is not possible because there is no address translation service for both CPU and the GPU. It won't happen. It doesn't work. Now, how does it work with the Grace Hopper? In Nvidia Grace Hopper superchip systems, ATS has been extended. There is the extended ATS service. Basically, ATS is part of the PCIe standard. ATS is part of the PCIe standard. The ATS service for Grace Hopper enables the CPU and the GPU to share a single process page table, enabling all CPU and GPU threads to access all system allocated memory which can reside on physical CPU or GPU memory. Okay, so here, this is the situation, is that there is this ATS service. It has been extended. There is this NVLink C2C. I've said that we have this PCIe 5, generation 5, running on top of this C2C link. And in the PCIe standard, there is the ATS is part of the PCIe standard. And for Grace Hopper, this standard has been extended. With this extended ATS service, the system page table has been unified. I mean, this GPU and GPU, they have the unified system page table. That means right now for CPU and GPU, both of them, they have the access to the page table. If the CPU needs to read virtual address, the page table is going to look up this page table, and it's going to find out this physical address. It can go and read this data here. This happens with the CPU memory and also happens with the GPU memory. And this same story is going to happen with the GPU. It can read this GPU memory and it can read this CPU memory. Okay. So with this, right now, this is the feature we have I have mentioned is that that you have 512 gigabytes memory here. You have 96 gigabytes here, HBM memory, and this HPDDR5 memory, and the total is 600 gigabyte memory totally. So the CPU and the GPU, both of them can access all the memory with this kind of extended PCIe ATS service. Right now it happens. Now we know it works with Nvidia Grace Hopper, and then we know the reason why it works. If you still remember in section 3, I mentioned that there is a kind of asymmetry because what? Because in section 3, I mentioned that the CPU can access the host memory, and the CPU can also access the GPU memory, but the GPU can only access its own memory, but not the host memory. There is a kind of asymmetry regarding the memory access for CPU and GPU. In section 3, when we were talking about these GPU computing systems with GPUs in the form factor of PCIe adapters. Now, it should be easier for you to understand why it doesn't work, why there is this kind of asymmetry, why the GPU cannot access the CPU memory, because there isn't this kind of extended ATS service for GPU and the CPU. So one of them, that's the GPU cannot access the memory of the CPU. Okay, so this explains both of them. Let's move on to have a little bit more technical detail of this ATS service and something called SMU. SMU stands for System Memory Management Unit. Okay, so this is a system management unit. Okay, we start from this one. This is a PCIe device. PCIe device could be a NIC adapter. For our case, this is the CPU. Okay, and this is the PCIe root port with ATS. This root port, pretty much, this root port should locate in the with the host with the CPU, with the CPU, with the grid CPU. For our case, it's located with the grid CPU. Then, if the PCIe device wants to read the CPU memory, basically, it relies on the ATS service to do the address translation. With GPU, it doesn't. It needs to read a virtual address. It needs to read a virtual address, and the virtual address doesn't point to any physical address. If it's not in this cache, this is address translation service cache. If it's not in the address translation service cache, the virtual address needs to be translated into physical address to read the data. To read data. So GPU, if it's not in its cache, it has to be translated into physical address, and the GPU cannot do it. It has to ask for the others to do it. So it is going to send its ATS translation request to the PCIe root port with ATS service. And this ATS service translation request will be sent to SMU. SMU is the System Memory Management Unit. And the System Memory Management Unit is going to reply with the translation. And then the translation will be sent back to the GPU. Right now, is going to put it here. So right now, the GPU has the virtual address translation done, and is located in its cache. Right now, the GPU can use this translated hardware address to access the memory, and this is the ATS. The ATS is here. This explains how ATS works, and here we have we are saying the Hopper GPU is going to consult this system page table to have this translation, because the translation is within this system page table translates the address. But basically, the unit which is going to do the translation for GPUs is this SMU. The SMU, for sure, it should be able to consult this page table. So here is the documents from the ARM website. ATS extends the PCIe protocol to support an SS SMMU that translates DMA address request in advance. The translated address are subsequently cached in the ATC. The local translation look-aside buffer is named as ATC. Now, the locating translated address in the device is to reduce latency and provide a scalable distributed computing system that improves I/O performance. So if the GPU needs to do the translation very often, if the translation has been done, it's better to put translation in its ATC. And the second time, when it has to read this address, the translation is already done. This is what has been said, is described here. Okay. Now, a very quick look of this SMMU stuff. You know, we have this P. P means CPU. Most time it means CPU. The CPU basically there is memory management unit which works very closely with the CPU. When the CPU need to read an virtual address, the MMU is going to do the translation. So, and then it's going to access the memory. But in section 3, we have mentioned that the CPU has the right to read the memory of the device. That means pretty much means that the MMU has the translation for the CPU. It can translate the virtual address into this GPU address. Device means GPU for our case. So GPU. So that explains why CPU can access the GPU. But if there's no SMU, the GPU has no address translation. It cannot access the system memory. That's only with this SMMU, the system memory management unit, the GPU has got the possibility to read this GPU memory. Okay, so SMU performs a task like that of MMU in CPU. It translates address for DMA requests from system I/O devices before the requests are passed into the memory interconnect. The SMMU only provides translation services for translations from the client service, from the GPU to CPU, not for translation to the client device. Translation from system or PE to the client device are managed by other means, for example, the PE. So translation from CPU to GPU is done by MMU. And if MMU can do the job, that means CPU can access the GPU memory. If you have the SMMU, you can access the memory by doing this translation. Is the key part of the address translation service. If there is no this service, this pretty much the case for the GPU computing systems with GPUs in the form factor of PCIe adapters. That are the systems we discussed in section 3. In section 3, we said that the GPU cannot access the CPU memory. Pretty much the reason is that for the x86 systems, there is no this extended ATS service. Pretty much there is no SMMU for service for these GPUs. But this is a little bit the technical detail for the ARM CPU with this SMMU and with this extended ATS service. Right now, the CPU and the GPU can access each other's memory. Okay. We move on to this extended GPU. Okay. The extended GPU memory is called GPU. This feature, utilizing the high bandwidth NVLink C2C, facilitates efficient access to all system memory-based GPUs in a single node system. So a single node system means GPU and CPU and GPU connected by the C2C. EGM applies to integrate CPU, GPU, Nvidia system by allowing physical memory allocation that can be accessed from any GPU thread within the setup. EGM ensures that all GPUs can access its resources at the speed of either GPU CPU NVLink or NVLink C2C. Now, in this setup, memory access occur via the local high bandwidth NVLink C2C. For remote memory access, CPU, GPU NVLink, and in some cases, NVLink C2C are used. Okay, we stop here. We are going to discuss the others in the next section, but we are going to leave all this in the next section. But here is that basically is saying this EGM feature of the GPU is that normally the GPU, we come back to this to this picture. Now, the GMMU, that's GPU memory management unit. Basically, it should manage this memory. If there is no cache coherent, if there is no ATI service, it only manages this HBM memory. So it won't care how many memory you are going to have here from the host side. It's going to, the GPU relies on the GMMU can only use its own memory. Now, that means Nvidia has worked with their GMMU, worked with their GPU. It has improved its GMMU unit. That means right now the GMMU can manage the HBM and plus the memory from the host side, this memory. So it seems from the point of view of the Hopper GPU, right now the GPU has a kind of extended memory. The memory, the HBM memory has extended to include this DDR memory. So the global memory, all this memory, it seems that's also part of the GPU memory. This is called the extended GPU memory. So this feature, basically this feature is the summary of all the things we have discussed. It relies on the ATS service. It relies on all this stuff. SMU, ATS, NVLink. It relies on this stuff to make the GPU memory really extended to cover the similar memory. Okay. Anyway, right now, right now it seems it's a little bit a feature for commercial purpose. But later on in the next section, we are going to come back to this EGM feature again. In that part, we are going to discuss more heavily this EGM feature because it's going to get more interesting and more difficult to understand and more challenging to program the system. Well, for the moment, okay, we know that the EGM feature means that the GPU can access the memory of its own plus the memory of the host of the CPU. Okay, this is the EGM feature. Okay, we have covered these features, and these evolutions, all this stuff, NVLink, C2C, ATI service, SMU, EGM, extended GPU memory, all this, we put everything together. What's the benefits for the programmer? The benefit for the programmer is this one. With this address translation service, CPU and GPU memory, CPU and GPU can access each other's memory. That means right now, the life is going to be easier for the programmer because there is no more need to copy the data from the CPU to the GPU and from the GPU back to the CPU. Okay, now let's have a look at this code example. This is a kernel function. Kernel function is a function that's going to execute on the GPU. And here we this is a kernel function call, and this is called by the host, by the CPU. By call this kernel function, the host is going to pass to this kernel function these parameters. And x and y we know are two vectors, two one-dimensional vectors. This is x and y. And where is x and y located? X and y is located in the CPU memory. Here is x and y located. X, y is located here. Okay, and then I'm going to call this kernel function. Kernel function is going to be executed here. The kernel function is going to be launched. It's going to be executed on the GPU. And to access the X and Y, it just access the X and Y because the GPU can access the CPU memory. That's the kernel function call with superchip. But if you still remember, that's not the story for GPU computing systems with GPUs in the form factor of PCIe adapters. And that's not the case. It's not the case for the GPU computing systems with Nvidia SXM modules and AMD OAM modules, because at that time the GPUs are connected to the CPU by purely a PCIe link, and there is no access from the GPU to the CPU memory, from GPU to the host memory. If the CPU cannot access, the GPU cannot access the host memory for this piece of code to work, there are some lines of code that has to be written by the programmer. We have discussed that in section 3 and 4. The fact is that this XY is located in the host memory. If the kernel cannot access this memory, if that cannot be done, the programmer's responsibility is to copy the X to the GPU. It's called DX. It has to copy this Y to the GPU. It's called DY. It's Y on device. It's called D_Y. So that means to call this kernel function, you have to do copy. So CUDA mem copy function, etc., etc. And then you have to copy from X to DX this function call, and then you have got to the memory copy Y dy. This is you have to do, and this Y to dy, because you ask the kernel to work on the data has to be located in the GPU memory because the GPU cannot access the CPU memory. And for this kernel to work correctly, you have to do the memory copy. And here your call will be with D_X and D_Y with these two parameters. And after the job has been done, you have to do CUDA memory copy to copy the data back from GPU memory to host memory. Suppose you want to put the result in Y, you have to copy it back. And these are the lines of code you have to write. To deal with the old systems. All the GPU computing systems, except this Grace Hopper. Because Grace Hopper, this problem doesn't exist anymore, as shown by this piece of code. Okay. So we are reaching to the end of the discussion of the Grace Hopper superchip. So Grace Hopper superchip and the Grace Blackwell superchip later on there is a very important evolution. There are some very important technical evolutions, technical advancements. But at the end, my conclusion is that GPU is still a PCIe equipment. This is a quick solution for Nvidia. Okay, this cannot be done with x86 systems. It can only be done with the ARM systems because the business model of x86 x86 is pretty much the property of Intel and AMD, and Intel and AMD are the direct competitors of Nvidia. Uh, I have the doubt that the x86 standard will be totally open to Nvidia. So they cannot have all this done with x86 systems. The only solution for them is to have this GPU hooked up with the ARM CPU, the Grace CPU, the ARM CPU. And we have seen all this throughout the discussion because we have seen this AMBA CHI protocol, the cache coherent protocol from ARM. So this is the protocol that Nvidia has licensed from ARM. At the same time, it worked with its GPU, and Nvidia has extended these PCIe standards. Notably, they have done this ATX extension to make the CPU and the GPU can access each other's memory. So these are all very important technical improvements. That's going to make the life easier for the programmers, much more easier. We are going to discuss this later on. That open up the doors for Nvidia to have new market shares for new applications. We are going to have a look in the next section. But at the end, my conclusion, GPU still is a PCIe equipment that's connected to the ARM CPU. That's still PCIe equipment. And that means GPU is talking with this CPU by this PCIe protocol. But this PCIe protocol has been improved, has been evolved. So that means at the same time, the CPU can access the memory of GPU and the GPU can access the memory of the CPU. Okay. And then at the same time, things are more advancing more faster, more features has been added to this kind of connection between the CPU and the GPU because this cache coherent protocol from Grace has been deployed. Also, on top of this NVLink C2C links. So Nvidia has replaced the old, the PCIe physical link because the GPUs were always connected to the x86 by using the PCIe links and the PCIe protocols and the PCIe links. And right now, Nvidia has replaced the PCIe link. Normally, for x86, we use PCIe link. For ARM CPU, they have dropped this PCIe link. They replace this PCIe link with the NVLink. And the NVLink is supposed to be much more faster than the PCIe link. But still on top of this NVLink C2C, what we have is still this PCIe Generation 4 protocol, with the extended ATI service. And on top of that, you have got this cache coherent protocol comes from ARM that has been deployed between the two. And now the CPU and the GPU is same. It's very much it's pretty much like a coprocessor to the grid CPU, but it's connected to the CPU by this PCI link. So at last, the conclusion is that with all these advancements of the technology, with all these evolutions, the performance has been dramatically improved. And by the end, there is no architectural revolution because GPU is still a PCIe equipment. But this doesn't affect the 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 business of this super chip. That's very simple. It works, even it's not a revolution. I'm comparing this solution with the AMD solution. I'm going to come to the AMD solution in the second in the next part. We are going to have a look how AMD has worked on with their systems to produce a product which is pretty much the MI300A, which competes directly head-to-head with Superchip on the marketplace. Okay, so this is the end of this part of discussion. There are some very important evolutions, no revolution, but it works. Even though that GPU is still a PCI equipment connected to the CPU. Okay, let's stop. Let's have a rest for 5 minutes, and then we are going to continue again.